Welcome everyone to another TCS Plus talk. So today is a great pleasure to have Haotian Jiang from the University of Chicago, who's going to tell us about Beck-Fiala and Komlós bounds and problems in discrepancy theory. Um, and well, before I hand the floor over to Haotian, I do want to encourage everyone to if you can, keep your cameras on. I know that giving talks through Zoom can be much more engaging if people are willing to turn their cameras on and make the experience better for Hartian. And I'll mention that, I mean, TCS Plus, we're an online seminar we've been running now for over 10 years, and we're always looking forward to suggestions. So if you know of some interesting result in TCS that you think would make a good TCS Plus talk, please, there's a suggestions form in our website. So please go ahead and send us your suggestions, and we'll be happy to have them as talks. With that being said, the talk is being recorded, but there will be an unrecorded session after the talk where we can ask Hatian some further questions or discuss the results. Then with that, I'll hand over the floor to Hatian and then please take it away.
Okay, thank you very much, Eric, for the introduction, and thank to the organizers for inviting me to give this talk. I'm going to tell you some recent progress on the Beck-Fiala and Komlós conjectures, and this talk will be based on joint work with Mikhail Bunso from the University of Michigan. Good. So, we'll discuss combinatorial discrepancy and what this is. So we're given a universe of n elements and sets S1 to Sm. And our goal is to color the elements red or blue so that every set in this set system is as balanced as possible. Okay? More formally, given any m by m matrix A, okay, this A can be a general matrix, but in order to capture, for example, the system above, you can think of A as its incidence matrix. So this is an m by m matrix whose rows corresponds to the sets and columns correspond to the elements. And then entry is 1 if the corresponding column element lies in the set which corresponds to its row. Okay, and 0 otherwise, right? This is what incidence matrix are. Um, okay, so for an arbitrary matrix A, okay, generally, the discrepancy of A is defined as the minimum of the L infinity norm of AX, where X is over all the plus minus 1 vectors. So why does this capture this balanced coloring intuition above? Well, you think of X as your coloring, okay, where minus ones are the red elements and ones are the blue elements. Okay? And now every coordinate of AX, of course, is some row of A, right? It's this row inner product with the coloring X. And because this row is just the indicator of some set, this inner product is simply the difference between the number of blue and red elements in this row or in this set, right? So the L infinity norm is basically the worst imbalance over all the sets in your set family. Okay, so this indeed captures this right notion of balanced above. Um, okay, and now let's take a slightly different but equivalent one to Vn. These are the columns of your input matrix. You want to find a plus minus one signing of these vectors to minimize the L infinity norm of the sign sum. Okay? So these kind of questions of splitting objects into two similar parts, they're both natural math questions by themselves, and also they have many applications, like say to randomized controlled trials, sparsification, rounding, machine learning, complexity, and many others. And I won't go into these applications, but here are some standard references, textbooks that you can look into if you're interested. So one thing is that for any kind of these discrepancy problems, you can always pick your coloring to be a uniformly random plus minus one coloring, right? But this kind of ignores any structures of your problem. And so discrepancy theory is all about being random, and often you can do much better than this kind of random strategy, and surprisingly, even without any structure. So here's an example what I mean by that. It's called Spencer's problem. So in this problem, you have n sets and n elements. So in this set family view, m is equal to n. So random coloring would give you a discrepancy of square root of n times square root of log n, right? Throughout the talk, we're going to ignore constants. Um, okay, so why is this the case? Because for every set, uh, using standard concentration, the discrepancy of every set is c times square root of n with probability exponential minus c squared, right? Square root of n is the standard deviation. You have a Gaussian tail by standard concentration. Now you can take c to be some constant times square root of log n, and you can apply union bound. Right? This shows that actually with high probability discrepancy, square root of n times square root of log n. Okay? But surprisingly, Spencer showed that this union bound loss of constant times square root of log n is not necessary. You can avoid it, and you can always find a coloring with discrepancy only a constant times square root of n. So this is very surprising because a priori there's no reason that this is even possible. And now that we know that only exponentially small fraction of colorings achieve this, right? So it's not a typical behavior. It's extremal behavior in a sense. So the proof of Spencer's proof relies on this very general method called the partial coloring method. I won't define what this is because we don't really need this for the rest of the talk. But this was initialized by Beck in the 1980s and strengthened by Spencer. And this uses some kind of entropy plus pigeonhole principle argument. So there's an alternative view by Gluskin of the partial coloring method using convex geometry approach a few years later, kind of independently. Okay, so this is so in Spencer's problem, there's kind of really no structure assumed except for the number of sets equal to the number of elements. But if you actually have some structure, you can actually do substantially better. And here's a very natural kind of structures, which is low degreeness. And this is called Beck-Fiala problem. So in this problem, again, we have a set system, and now each element lies in at most k sets, right? Where you can think of k as something really small, some parameter. Okay? So in other words, this matrix A is a 0, 1 matrix with k column sparsity. And one thing is that we can always assume that M is equal to N, the dimensions match. I will get back to this point shortly. Um, so note that this is generalization of Spencer's problem. You can set k equal to n, and you recover Spencer's problem. Okay? So again, random coloring would have a discrepancy of at least square root of n, right? If you have any row, any set which has at least a linear number of elements, it's typical discrepancy square root of n, right? Constant times square root of n. But Beck-Fiala showed that you can do actually substantially better. You can get a constant times the sparsity k using linear algebraic argument. And they conjectured that the correct answer should actually be square root of k, which would nicely generalize Spencer's result for all possible k. Okay, but this is actually a much harder problem. In fact, Spencer used the same partial coloring method and get a square root of k times a log n bound. And this was later improved by Banaszczyk in 1998, who gets a square root of k times square root of log n using deep ideas from convex geometry. Okay? And sort of the current best bound is kind of a combination of this Beck-Fiala constant times k and Banaszczyk's bound, depending on how large k is. But the point is that for k being log n, this is actually where these two bounds meet. The current bounds are all log n. Right? And this is really the kind of the point where we kind of going to discuss any improvement. So let's keep this in mind. Okay, so we can actually take this problem, like generalize this problem one step further in this vector balancing view, right? This is called Komlós problem. We are given unit vectors v1 to vn. Each one has L2 norm, Euclidean norm at both 1. Right? In other words, your input matrix A has unit length columns. And this is a generalization of the previous Beck-Fiala setting because recalling Beck-Fiala, you're given this K, this A is a 0, 1 matrix with column sparsity K. Right? So that means the column has L2 norm square root of K. Now, if you scale down the matrix by this 1 over square root of K factor, this will get you an instance for the Komlós problem. Okay? So this is really a more general setting. So Komlós conjecture that the discrepancy of any set of unit vectors should be a constant. And by the same reduction, this is actually a stronger conjecture. This conjecture, Komlós conjecture, implies the Beck-Fiala conjecture. And that square root of k really comes from this scaled down factor of 1 over square root of k to go from Beck-Fiala to a Komlós instance. Okay, in the same paper, Banaszczyk's method gives a square root of log n bound. And this has been the best bound for the Komlós conjecture since then. So it turns out that there is no clear consensus on whether people really believe in this conjecture or not. In fact, Hajela conjectured that this later bound of Banaszczyk should be tight up to a constant. It actually gives some partial evidence why this should be the case. But despite a lot of effort, the current best lower bound for the Komlós problem is only a constant. It's 2.414 due to Kunicki. So I want to mention just in passing that there are a lot of other recent surprises about, other constant discrepancy conjectures. For example, for Erdős discrepancy problem and Beck's three permutation conjecture, Tao and Newman and Nikolov showed that these conjectures are actually wrong. Okay. So in this work, we actually give some positive evidence for Komlós conjecture. In fact, we showed that a log into the 1/4 bound up to a polylog-log factor, a log into the 1/4 bound for Komlós, and this improves Banaszczyk's bound since 1998. And this implies directly a k square root of k times log into the 1/4 bound for the Beck-Fiala problem for all k. And in fact, for Beck-Fiala, we can actually say something stronger. In fact, we can prove the Beck-Fiala conjecture whenever k is at least log n squared. Previously, the conjecture was only known for k roughly equal to n by Spencer result that we mentioned earlier. For smaller k, we can get up to a polylog-log factor, square root of k plus a square root of log n bound. And essentially, this replaces Banaszczyk's square root of k times square root of log n by a sum. And you can immediately note that this, compared to Beck-Fiala conjecture, this bottleneck is this additive square root of log n term, right? And in fact, if you can remove this or further improve on this additive square root of log n, that might likely lead to a direct improvement to the Komlós bound. That's where the bottleneck really is for all these results. Okay, and all our results admit efficient algorithms. You can actually give a polynomial time algorithm to find a coloring which matches these discrepancy bound. And in fact, our proofs are crucially based on efficient algorithms. So let's talk about this algorithmic aspect of discrepancy. So partial coloring method by Beck, Spencer, independent by Guskin, and Banaszczyk's method originally were existential. That means they only showed that low discrepancy coloring existed, but they did not give any efficient algorithm for finding a coloring that matches those discrepancy bound. Okay? But over the last 15 years, there has been a lot of development on giving efficient algorithms, and now we can sort of have many algorithms that achieve partial coloring and Banaszczyk's approach almost in their full generality. Okay, and in fact, our results are built on top of this first work, the second sort of bullet point, this Bansal, Dadouche, and Garg's work, which give the first algorithm that matches Banaszczyk's bound for the Komlós problem. So we'll be building on top of this algorithm. Okay, here's the plan for the rest of the talk. So as a warm-up, we're going to kind of recall what is Beck-Fiala algorithm, which achieves a constant times k discrepancy, and also this BDG algorithm, which gets Banaszczyk square root of k square root of log n bound for Beck-Fiala. We're going to discuss why these algorithms are stuck where they are and discuss new ideas. And then we're going to describe a basic version of our new approach, which gives a square root of k log n to the 1/4 for Beck-Fiala. Okay, and we're going to focus on this k equal to log n regime earlier and prove an improved bound of log n to the 3/4. So recall all previous bounds were log n, so this already gives a non-trivial improvement. And finally, I'm going to mention some extensions, which gives this log n to the 1/4 bound for Komlós and our stronger bounds for the Beck-Fiala. Okay, are there any questions from the audience so far before diving into the technicalities? Okay, if there are no questions, let's recall the Beck-Fiala settings, right? So we're given this input 0, 1 matrix A, which has k column sparsity. And as I mentioned, you can assume m equals to n without loss of generality. Okay, a very simple way that you can do this is you pad A with zeros to make the dimensions match. Okay, of course, if the dimension m and n that you start with are very, very different, this is very non-efficient, right? It turns out in those cases where n is much bigger than m, and vice versa, you can do something smarter. But let me not get into this technical nuance here. So let's assume m equal to n, and what column sparsity really gives you in terms of rows is an average row sparsity, right? Because if you look at A and count how many ones are there, and because there are at most n times k ones, because k ones per column, and because m equal to n, this shows that the average row size is at most k. Okay? In particular, rows with sizes that are much larger than this average are actually problematic. And we'll call a row large if its size is at least 10k. And there are the most n over 10 such rows because the average row size is k, right? So they're at most n over 10, which is more than 10 times the average. Okay, so here's why the large rows are kind of the problem. If A had no large rows to begin with, then note that any coloring has discrepancy constant times k. And if you do a random coloring, okay, because row sizes are k, now standard deviation will be square root of k if you do uniformly random coloring. So this gives a discrepancy square root of k times the square root of log n due to the same union bound. So in a sense, without large rows, Beck-Fiala's bound and Banaszczyk's bound, you can do them kind of very easily. Okay. So really, the new idea in Beck-Fiala is that you can pretend that large rows do not exist by walking orthogonal to them. I'll explain what this means in 2 slides. But in the modern algorithm design language, this is called iterated rounding. Okay, so I'm going to discuss Beck-Fiala's algorithm in a slightly different way they phrase in their original paper, but I want to put everything in the kind of same algorithm framework. It's really equivalent to their original algorithm. So here's the general algorithmic framework for this, widely used in discrepancy. So you look at this unit hypercube, -1, 1 to the n, and you think of every vertex. Every vertex is a plus minus 1 vector. Every vertex is a coloring. And you want to compute a coloring by starting at the origin and do some kind of random walk until you hit one of the vertices. Right? That will be the coloring the algorithm computed. And one property I want to maintain is that once a variable reaches plus minus 1 throughout this process, it will stay fixed forever afterwards. Right? Or kind of in this geometric view, whenever you reach one of the facet, you're going to stay on that facet. Okay? Any elements that get colored, you won't change it afterwards. So let's fix some notations to talk about things. Xt is the fractional coloring at time t, which is going to get updated in every step t by a tiny mean zero Gaussian delta xt, whose covariance we denote as sigma t. Okay. The power and flexibility of this framework come from you can choose sigma t adaptively, depending on where you are, right? What is your history? So let NT denote the number of alive coordinates or live elements, meaning that they have not yet reached plus minus 1, right? And by this property above, only alive coordinates are updated, right? Once they reach plus minus 1, they will get fixed forever. So we only update those who have not yet reached plus minus 1. We'll let A1 to AN denote the rows of the input matrix A. And let DTI, which is the inner product of AI and XT, let this be the one-sided discrepancy of a row I. It suffices to control one-sided discrepancy. You can simply append the negation of every row into your matrix. Okay, of course, that creates -1 entries, but it's okay. The algorithm can handle it. So let's only control this one-sided discrepancy for now. This the discrepancy of row I is updated, of course, as the inner product of AI and delta XT. Okay, good. So here's the Beck-Fiala algorithm. Let's call a row large at time t if it has more than 10K alive elements. Okay? And by the same averaging argument, at any time t, there can be at most nt over 10 large rows. Right? This is the same kind of counting. You look at all the alive columns now, and because each one has k elements, there are k times nt alive entries inside your matrix restricted to alive columns. And then you do the same averaging. Right? There cannot be more than nt over 10 large rows at any time. So now here's the algorithm. You just always walk orthogonal to the large rows. More formally, let Wt be the span of the large rows AI, right? The dimension of this is in most nt over 10 by the observation above. And you just do an arbitrary step orthogonal to Wt. Okay? Well, equivalently, we're going to say Wt is blocked. So, okay, so this is the algorithm. You do this until you reach a vertex. And here's a picture proof or picture analysis of this algorithm. Okay, so here I'm looking at a fixed row, and I'm kind of tracking how much the discrepancy is incurred with this row as its size changes. Okay, because the sizes of the row or number of live elements in the row monotonically goes down as the algorithm progresses, right? So you should really look at this picture from the right to the left. So in the beginning, while the row is possibly large, it occurs zero discrepancy as long as its size is at least 10K, right? Because we're walking orthogonal to all the large rows. But now, once they become small, when their size becomes smaller than 10K, okay, whatever we do, their discrepancy can be at most 10K trivially, right? So this is how you get the 10K bound. Okay. Um, okay, so now how do you get this square root of K times square root of log n? How you get this kind of random-ish bound for Banaszczyk? Okay, well, here's the first step. So recall that if there are no large row, simply doing a random coloring would already get you square root of K times square root of log n discrepancy, right? And in Beck-Fiala, we show that, okay, the idea is that you can simply walk orthogonal to large rows and pretend that there are no large rows at any time. So how about let's just walk randomly and orthogonal to the large rows, right? Maybe this would already work. So basically delta xt is now a uniformly random step in WT perp, right? And no, this looks promising because WT has dimension NT over 10. So this WT perp has very large dimension, right? It's a linear dimension. Okay, so here's the analysis. Um, while row I is large, again, it can occurs zero discrepancy. And for all the small rows, because delta xt is sufficiently random because it's working in such a large subspace, okay, maybe with high probability, it should only incur a square root of k square root of log n discrepancy as if we're taking a uniformly random step. Uh, but unfortunately, this analysis is incorrect. And the trouble here is that because you're walking in the subspace WT perp, this necessarily like introduces some dependencies among the coordinates of delta xt. So the second part is actually incorrect. So here's an example why it fails. Let's say WT perp enforces that the update to the first zero point 0.1 NT coordinates are all the same. Okay, so this is our WT perp. Okay, now let's say there is a row which corresponds to the first k elements, right? And then once you do this update, when you do the update step, let's say k is smaller than 0.1 nt, then that every element in this set must be updated by either all plus epsilon or all minus epsilon, right? As you take a step. So the discrepancy change of the set is epsilon times k, right? But on the other hand, we actually want as epsilon times square root of k if you update everything independently and uniformly at random, right? So this seems to be a much larger discrepancy update and seems fatal. So it turns out that surprisingly, we can actually design a smarter update delta xt that looks random in every direction, and hence for all the discrepancy of all the rows AI. Okay. How would we handle this example above? Well, you just set the first 0.1 anti-coordinates to all have an zero update, right? That would already take care of this issue, and this only consumes 0.1 degrees of freedom. So you can still have sufficient random free degrees of freedom to do a random update. But more generally, how do you do this? And this is sort of the notion called spectral independence. So BDG proved the following theorem. Suppose W is a subspace with dimension at most epsilon times n. Think of epsilon as something like 0.1 n. So it's a small, as epsilon is 0.1, so it's a small constant. They show that you can find a random update delta x, so that delta x is orthogonal to W. And also, the covariance of delta x is PSD bounded by 1 over 1 minus epsilon times the diagonal of the covariance of delta x. Okay? The second property is called spectral independence. And just want to mention that this notion was also kind of independently used in the sampling literature very successfully for say, sampling from high dimensional expanders. But it's really the same kind of notion. Okay, what does this really mean? What does this covariance delta x bounded by diagonal covariance really mean? So let's take an arbitrary direction A, right? Arbitrary vector A. So if you write out this, hit this both sides by this A transpose times the matrix times A, this is giving you that expectation of sum of AI delta xi squared. This is at most 1 over 1 minus epsilon times the sum of AI squared times the expected uh, delta xi squared. So the point here is that the square outside of the sum gets moved inside in the right-hand side. Okay, what is this? What is this really saying? So suppose you replace this 1 over 1 minus epsilon, is a constant anyway, by 1, and you replace this upper bound by equality. Then this is exactly saying that the delta x1 to delta xn are pairwise independent. Right? So really you should think of this spectral independence as saying that delta x1 to delta xn are almost pairwise independent up to this 1 over 1 minus epsilon factor. Okay, and it turns out that this is, okay, it seems very weak, right? It's almost pairwise dependence, but it turns out it gives that the discrepancy of each row has a Gaussian tail as we hoped already with this, it's already sufficient. It's shown by BDG. So the proof of this theorem is that you can write this delta x, the covariance of delta x, as a semi-definite program, and you can prove that there exists a solution using SDP duality. And this also gives you an efficient way to sample such delta x. You basically compute its covariance and do a random projection. Okay, so now here's the BDG algorithm. At any time t, You always block the large rows as before, but now you generate a spectrally dependent delta xt in the orthogonal subspace by solving this semi-definite program. Okay? So here's the analysis. Again, let's look at this picture here. So as when the row size is large, it will have no discrepancy as before. And because now this update has this constant spectral independence, so it gives that the discrepancy of every row has a Gaussian tail. So the probability that for when the row becomes small, the probability that the discrepancy of row I is at least theta times square root of k is at most exponential of minus theta squared. And again, you can take theta to be constant times square root of log n and do a union bound. And this recovers Banaszczyk's square root of k times square root of log n bound for the Beck-Fiala problem. Okay? And really the punchline here, if you want to summarize all this, what everything here is doing in one sentence, you can both walk orthogonal in a subspace and still look sufficiently random. Okay? This is really the idea of the power of the spectral independence. Okay. Any questions so far about this Beck-Fiala algorithm or the BDG algorithm? Everything makes sense so far? Okay, perfect. Where do we improve? So recall that BDG is doing this blocking large rows and generating spectrally independent updates. And this makes sure that all the discrepancy of all the small rows have a Gaussian tail. Okay, but you can also say, do something better, right? You can maybe say block NT over 10 rows with the highest discrepancy, right? You can do this for free. You have sufficient degrees of freedom. And this is very useful in general. For example, like Lovett-Mecha algorithm is crucial to achieve Spencer's result algorithmically. But the trouble here is that it's not clear why this helps in the Beck-Fiala setting. So let's say you want to achieve theta times square root of k, where theta is, say, log n to the 0.49, as in slightly better than Banaszczyk's bound. Roughly speaking, n times e to the minus theta square rows will hit this target discrepancy, right? You have this Gaussian tail, so every row is hit the target with probably e to the minus theta square. So this is the expected number of rows. And we call these rows dangerous if they hit the target. Okay, so how large is this number? Right, it's definitely much smaller than n, but it's not too much small if theta is like, say, log n to the 0.49, right? It's at least n to the 0.99. Right? So in the beginning, it's fine. You can block all these dangerous rows as you wish, but as everything gets colored and the number of live elements decreases, you run into a problem. What happens when NT is much smaller than n times this e to the minus theta square, right? What do you do? And it turns out this is where all previous approaches get stuck. It's not clear what we should be doing at this point. Okay, so in order to get around this issue, let's first, think about this hypothetical scenario where all rows evolve independently. Okay? Of course, the trouble is that this cannot be the case because the discrepancy of every row is driven by the same underlying update to the coloring, right? So all the rows are far from independent. They're very, very correlated. But let's, put this issue aside for a bit. A bigger problem, it seems, is that this is not buying you anything, this assumption of the rows being independent. So I can throw you the same argument and argue that this is not helping. So let's say you want to get discrepancy, again, like say log n to the 0.49 times square root of k, right? Roughly n times e to the minus theta square will become dangerous. What to do when nt becomes smaller than n times e to the minus theta square, right? It seems to be the same issue as before. But surprisingly, you can already get an improvement here, despite this issue. In fact, I'm going to show you how to get log n to the 2/3 for k being log n. And recall that, Banaszczyk gives you log n. So this is improving Banaszczyk by a log n to the 1/3 factor already. Okay, so here's our goal. And we're going to view this log n to 2/3 target discrepancy as theta times square root of k, where theta is theta is going to be set as log n to the 1/6 in hindsight. Okay, so let's call the row dangerous if the discrepancy reaches this target, log n of 2/3. So here's the key claim. At any time t, at most nt over 10 dangerous rows is going to have size larger than 10 times b. Okay, what is this bound on the sizes? B is defined as log n over theta squared. And this is by our choice of theta being log n to the 1/6. This is log n to the 2/3. And this is exactly the target discrepancy. Well, in fact, we set theta to be log n to the 1/3. Set theta to be log n to the 1/6 to make this log n to the theta square being the target discrepancy. That's how we set theta. Okay, so the point of this claim is that recall that n times e to the minus theta square rows will hit the target, will get dangerous, right? As nt becomes smaller, what this is really saying is that although still n times e to the minus theta square, which can be much, much larger than nt, a lot of rows will get dangerous, but only a very small number of them, only nt over 10 of them, will actually have large size. Right? So this is what this key claim is really asserting. I'm going to prove this claim in the next slide. For now, I want to, go tell you why this is already sufficient for our goal. So with this claim, here's the algorithm in this ideal world. At any time t, you're going to block large rows and generate spectrally dependent delta xt as before. Additionally, you're going to block all the dangerous rows whose sizes are bigger than 10b. Okay? And there are only nt over 10 such constraints of the third type by this claim above. Okay, so again, we go to this our favorite picture analysis of this algorithm. It's a bit more complicated, so let me explain this. First of all, when a row I is large, meaning that size is more than 10K, it incurs zero discrepancy, right? So this is the red the green part at the right side. And then once its size becomes smaller than 10K, well, okay, it's going to have this kind of Gaussian behavior, and some of them might get dangerous. Dangerous meaning that its discrepancy log into 2/3 or theta times square root of K, and it's the two red dashed lines here. This is really the boundary. Some of them might get dangerous. It might hit the boundary. Okay, but while its size is bigger than 10b, it's not going to incur any further discrepancy because we're blocking such rows, right? So this is really the green part here. And once its size becomes smaller than 10b, we are not blocking them anymore, so they can incur more discrepancy. But it's going to be harmless because it's at most 10b discrepancy afterwards, and b is exactly our target, right? Okay, so this is, really the difference is that, okay, a lot of the rows might hit this sort of boundary, but, we are going to block them so that um, only the rows with small size are hitting the target, they can incur more discrepancy. So really that's the kind of new argument here. Okay, so really the punchline is this key claim. Like, why can you say that at most NT over 10 dangerous rows have size more than 10b? Okay, so let's prove this. The probability, as before, the probability that every row I gets dangerous is e to the minus theta squared. And the key idea to prove this is to actually look at a fixed column J and ask how many of the entries in this column, how many the ones in this column would correspond to dangerous rows. So the probability that there are B dangerous entries in this column J is, I claim, is upper bounded by the following quantity. So K choose B is all the possible choices of B entries in this column. And for every fixed choice of B column, fixed choice of B entries, the probability that all these B entries correspond to dangerous rows is e to the minus theta squared times B. Okay? And this is why we set B to be log n over theta squared, is to make this probability, this first order computation, at most 1 over poly n. Okay? So with this, we can basically do a union bound over all the polynomial time steps and all the columns, and to say that at any time, uh, any column has at most B dangerous entries. Okay? Now we do our favorite averaging argument. So if you look at all the alive columns and count how many dangerous entries are there in total, well, they're at most NT over B, such red dots or dangerous elements. By the same averaging argument, you get that at most NT over 10 dangerous rows have size more than 10B as before. Okay, so this proves the key claim. Okay, so this is assuming everything is dependent. Of course, the reality is that the rows are highly dependent. Okay, but here's a new idea, right? In the same way that we can make sure that the update of the coloring is almost pairwise dependent, okay, we can simply make that the rows are approximately independent by adding some new SDP constraints. And this is called affine spectral independence. So recall that spectral independence says that the covariance of delta x is bounded by a constant times the diagonal of the covariance of the change in discrepancy, right? Of the change in coloring delta x, which roughly says the entries of this coloring update delta x is almost pairwise independent. Okay, now we care about the discrepancy of different rows. Let's say like this vector is dt. So delta dt, the discrepancy change is a times delta xt, right? And earlier we said if delta dt has independent coordinates, right? If your coordinates are updated independently, then we're in great shape. Okay, so a natural idea is how about let's just make the entries of this delta dt vector to be approximately or almost pairwise independent. In the same way that spectral independence, right? Guaranteed delta x has almost pairwise independent coordinates. Okay? And this is the new set of SDP constraints. We call this affine spectral independence. So for any given matrix A with m rows and n columns, we can add some new SDP constraints to ensure that the covariance of A times delta x is PSD bounded by this factor of m over n times the diagonal of the covariance of A times delta x. Okay? So if you look at this delta dt vector, which is A times delta x, this is a discrepancy update. This vector is spectrally dependent with this m over n factor, loss factor, and which says the rows are almost pairwise independent up to this m over n factor loss. Okay? Uh, and sort of this m over n is there's a technical issue here is that this m over n factor is actually unavoidable because really the more rows that you want to control, you need to pay some price, right? This factor here, dimension factor here is the price that you pay. Okay, but it turns out this kind of weak independence of rows, even with this m over n loss, is already buying you something. This already gives you some improvements. And so now I'm going to show you how to get a log into the three-quarter bound when k is log n, by using basically the same argument, but now with this weaker notion of the independence. So here's the basic method. Our target now is theta times square root of k, where theta is log into the 1/4, right? So this is log into the three quarters, for k being log n. And here's observation. You can discard all the irrelevant rows of size smaller than log into the 3/4, right? Because this, as before, all such rows can occur at most log into the 3/4, additional discrepancy, so they don't really matter. At any time, this makes sure that at any time they're at most empty they're at most empty, which is at most nt times log n to the 1/4 relevant rows. Okay? Why? Because the same argument. Look at all the nt columns, they're at most nt times k, which is nt times log n entries, right? And all the relevant rows have size larger than log n to 3/4 by the same averaging counting argument. This is what you get. So this means that you can ensure that delta dt is log n to the 1/4 spectrally independent but restricted to the relevant rows. You don't care about the other irrelevant rows. Okay, so now let B to be log into the 5/4 over theta squares, and you can prove a similar bound as before. So you can prove that for any fixed column J, the probability that B entries become dangerous is so it's a very similar bound, but you lose this additional NT over MT factor here due to this kind of weaker notion of independence, due to this spectral independence factor, right? And because now we set this NT over MT is like log into the one, like say 1 over log into the 1/4, and now we set B to be like log into the 1/4 more than the independent world. This is again a 1 over poly n probability. More formally, you can prove this as you can formalize this bound as a decoupling bound. It's a bit more technical to prove. It's not as just like doing some kind of union bound, but you can prove this by regularization plus the moment generating function, which I'm not going to dive into. Okay, so after this step, when you show that every column has the most B dangerous entries, you can use the same averaging argument to give give a log into the 3/4 bound. Okay, so really, just to summarize what happens, what are the new ideas here? The first idea is that if you assume that the row discrepancies are evolving independently, then you can show that every column has very few dangerous entries. Right? This means that although still there are a lot of dangerous rows, but most of the rows will actually have negligible sizes. Right? So you can afford to just control all those with larger than 10B sizes. Okay, and now you can basically get very close to this ideal world by ensuring that the row discrepancies are approximately independent by adding a new set of SDP constraints. And this weak independence already gives you some non-trivial improvement over the previous bounds. And this is a very flexible and robust framework, and we can give some further extensions. And so here's the first extension, getting this Komlós bound. So recall that this basic method generally actually give square root of k times log into the 1/4 bound for all k. Okay? And we can use this to get log into the 1/4 times the polylog log factor bound for Komlós. And basically, you can view Komlós as Beck-Fiala instances at various scales, where scale means how large each entry is, right? You do kind of dyadic scales. Naively, you would care about the entries in your input matrix. Okay, because every column now has L2 norm at both 1, right, in the Komlós setting. So naively, you would care about entries between 1 over n and 1. Right? So naively, if you do a dyadic scale, there are log n scales. But it turns out you only need to care about log n scales. This is because you can actually ignore entries of size much smaller than 1 over log n cube. And this is because the basic method actually gives a stronger bound if k is large. So if k is larger than log n cube, the basic method doesn't just give k, square root of k log into 1/4, it actually gives square root of k times a polylog log factor. Okay, so for all the entries of the Komlós problem with size smaller than 1 over log n cube, they lose a square root of log n bound, like by this basic method, and the rest is just log n scale. So you can kind of uh, in parallel handle them. But you need to some care to handle all the scales simultaneously because you're generating a single coloring for everybody. Okay? I won't get into these technicalities. So another so sort of the other extensions are how you get these stronger Beck-Fiala bounds. So recall that in the basic method, what we basically say is that if you restrict to the dangerous rows at any time, the column sparsity of the dangerous rows becomes something like B. And we set B to be much, much smaller than K so that we can block all the relevant dangerous rows, all the dangerous rows with size more than 10B, right? This was our argument. What for this to make, for this argument to work, we need the sparsity of these dangerous rows B to be much, much smaller than K. We need this B to be our target, right? But we don't really have to, rush to get this sparsity B down to the target. Instead, we can view the dangerous rows as another Beck-Fiala instance with sparsity B. Okay? And from this view, we don't have to directly block all the relevant dangerous rows with size more than 10B. Instead, we can basically recursively solve this Beck-Fiala problem with the sparsity B. And as long as sparsity B is smaller than K by a constant factor, right, this already makes some progress. So this is our kind of idea of a multi-level version of the algorithm of this framework. So what happens is that every row starts at a ground level, and whenever there are at certain times there are some dangerous rows that become dangerous. Whenever a row becomes dangerous, that dangerous rows get fed to an algorithm which runs in parallel at level 2. And level 2, the sparsity would become something like k over 100. Sparsity decreases, right? And dangerous rows at level 2 will get feed to level 3 and so on and so forth. So all these levels will be run in parallel and the rows move adaptively across the levels. Okay. But the point is that the sparsity of any set of rows which could appear at the upper level is going to go down geometrically. Right. So you can sort of think that everything becomes much, much easier as you go up this level. And if you do this carefully, this will give you a log into the square root of k. You can prove Beck-Fiala conjecture exactly for k being at least log n squared, and actually cover the ideal world result of log n to 2/3 for k being log n. So with this new idea, in order to push down one step further to get the square root of k plus square root of log n, we have some additional ideas, but it's a bit more technical, so I'm going to skip. So our current bound is kind of the square root of k plus square root of log n when k is smaller than log n squared. And this additive square root of log n is the bottleneck to this, to further improving this log into the 1/4 bound for the Komlós problem. And the reason we need to incur this additive square root of log n, roughly speaking, is because we need concentration. We want to say that there are very few dangerous entries in every column and also at every time step throughout the process, right? And the reason we have to do this because we don't really have control which are the NT elements that are surviving or that are alive at time t. Okay? Because the adversary can simply, so if you have some columns with more dangerous entries than you want, the adversary may just keep these bad columns alive, and there's this averaging argument we are doing doesn't work anymore. So it turns out that if you can get some kind of mild non-adversarial guarantees on which columns are alive, that would probably already be very helpful. Okay? But we don't know at the moment how to get such guarantees. Okay? So I want to finish the talk by mentioning some open problems. Of course, one of the most immediate open problems is, can you prove the Beck-Fiala conjecture now for all k, even for small k? So I didn't mentioned this earlier, but it turns out if A has no large rows to start with, you can actually random coloring. You can actually show that with positive probability, you show using Lavash local lemma, with positive probability, you get square root of k times log, square root of log k. Okay, and of course you use algorithmic Lavash local lemma to get an algorithm to achieve this bound. So this is already square root of k times log, square root of log n instead of the Banaszczyk's bound of square root of k log n, the square root of log n when k is small, right? And also we mentioned this intuition of Beck-Fiala that you can pretend the large rows don't exist by walking orthogonal to them, right? So it seems there's a natural hope that you would kind of bridge between these two ideas and get a square root of k times square root of log n bound for k being small. But the issue here is that right now the proof technique for Lavash local lemma and this walk orthogonal ideas are very different, and we don't know how to bridge them. And we're very interesting if there's a way to do this. So another set of related open problems is what's so-called prefix discrepancy problems. And just to give you an example, Banaszczyk in a later paper used similar ideas to show this falling stronger bound. If you're given unit vectors v1 to vn, Banaszczyk showed that there actually exists a coloring so that every prefix has discrepancy square root of log n. So not just, so you call that in Komlós, Banaszczyk said, oh, you look at all the vectors, the sign sum of all the vectors has L infinity norm as at most a constant times square root of log n. Okay. In fact, you can find a coloring so that the sign sum of every prefix is also achieving this constant times square root of log n bound. Okay? And the algorithmic question for this problem is much more interesting because right now we don't know of an efficient algorithm which matches this bound. So we only know the best algorithmic result is log n. And also, you may believe that Komlós conjecture would not be true if you restrict to prefixes, right? Because it's a much stronger guarantee, right? It can take infinite number of vectors. But it turns out surprisingly, existentially, we even don't know how to rule out a constant. So this is kind of widely open. And even the too sparse version of this problem is not known. And this is in particular motivated by a very nice paper of Bansol, Rueder, and Svensson, who gave a reduction from a scheduling problem to this prefix version of Banaszczyk, or actually too sparse version of Banaszczyk, prefix Banaszczyk. Okay, so there are other related questions with a prefix flavor. For example, there's the natural online version of these problems. What happens if your vectors are given online, right? Again, there are many open questions there. And there's also geometric settings, for example, Tushnadi's problem and approximating covariant discrepancy. Right now, we don't know how to generalize our kind of argument or techniques to handle this prefix constraint, despite the sparsity assumption in these problems. Okay, it'd be very interesting to kind of explore these directions. Okay, that's everything I want to cover. Thank you for your attention.
Okay, we can pause for a few questions. Maybe Haotian, can you mention again what would you hope to say if you combine these ideas of the Lavash local lemma with the Beck-Fiala intuition?
Yeah, that's a very good question. So I think if you, in the most ideal world where you can come up with some kind of proof which both gets you this Lavash local lemma for a bound for small k, the square root of k log k, and the all these other ideas I covered in the talk, you could possibly hope to get a polylog log n loss or polylog log n bound for the Komlós problem, right? By again doing these things at now every scale, not just not you like kind of truncate at some log into the to yeah.
I see.
Yes. Yeah. Yeah. So right now the kind of the bottleneck for Komlós is when k equals to square root of log n, and the bound we get there is not better than the Beck-Fiala bound. So for k equal to square root of log n, we can only get square root of log n, right, which matches this constant times k bound. But if you're able to do this, you can actually get log into the 1/4 there, so you can every scale you only lose polylog log instead of this log into the 1/4 mentioned earlier.